Hello everyone, welcome to the 12th live session of our course Semiconductor Devices and Circuits, which is being taught by Professor Sanjeev Samara. And this will be our 12th live session. So, in this live session, we will be solving the problems mostly related to the circuits. Okay, so let's start today's session. Okay, so let's begin today's session with the problem. Okay, so there were some problems that we had left previous time. So in the previous session we stopped right over at the problem 5. Now let's first, I guess there will be some 2 or 3 problems related to the uh, NMOS or the MOSFET itself, and after that we will start the circuits, the small signal analysis. Okay, so it states that we have to consider an N-channel MOSFET with these specs like W is 10 micrometer and length is 1 micrometer, and also the oxide capacitance and the drain bias is given to us, and the gate to source bias for two conditions is given, that is one is 2.5 volts and other is 1.5 volts, and the current levels are 100 microampere and 50 microampere. So we have to find out the mobility of the MOSFET, this transistor, this NMOS. Okay, first of all, you can see VDS in this case is just zero point 0.1 volt. Okay, and VDS is clearly less than, okay, and VDS is clearly less than both the VGS minus VTH, whether it's VGS minus you can say uh, VTH is the threshold voltage, whether it is VGS1 or VGS2. Okay, so you can say the device is in non-saturation region. Okay, device or NMOS is in non-saturation. Okay, so we can use the small VDS approximation, and we can simply write the ID1 to be equal to mu n Cox W over L VGS minus VGS1 minus VTH times VDS. Similarly, ID2 can be written as mu n Cox W over L VGS2 minus VTH times VDS. Okay, so if we subtract this ID1 and ID2, ID1 minus ID2 is simply, it will simply give me mu n Cox W over L VGS1 minus VTH minus VGS2 plus VTH times VDS. Okay, so VTH and VTH will go, and we will be simply left with ID1 minus ID2. ID1 is 100 microamps and ID2 is 50, so it will be 50 microamps. So it's 50 into 10 to the power of minus 6. Mu n we need to find out. Cox is 100 nanofarad, so it is 100 nanofarad per centimeter square, so it is 100 into 10 to the power of minus 9 times W over L. W over L is simply 10 over 1. W is 10, L is 1. Okay, so it is W over L, and it is simply 10 times VGS1 is 2.5 and VGS2 is 1.5. So it is simply 1 times 0.1. Okay, so it is simply this will go with this, and it will be this will be simply 1, and it will simply be 10 to the power of minus 8. Okay, so it will be 10 to the power of minus 8, so it will go over here, so it will be simply 500 centimeter square per volt second is the value of the mobility. So the option third option is the correct one. Okay, now moving to the some conceptual problem. I guess this we have seen many times, so I will just state it over here. So which of the following statements are true? The interface states affect the subthreshold swing of a MOSFET due to the presence of additional capacitance. This is absolutely true. We have seen how the oxide charges they change the threshold voltage values, and also how they affect the currents because of simply they are affecting the threshold voltage. Okay, they are affecting the interface charges that are going to respond to a particular gate bias. Okay, so they can either enhance the subthreshold swing or they can even degrade the subthreshold swing. Okay, so it will depend upon the type of the charge. Okay, so also the CV characteristics of a MOS system shift left or right based on the traps present in the oxide. This we have also seen how it can shift the oxide charges, can shift the threshold voltage, and how it can shift the CV curve, and this is also true. So presence of trap charges has no effect on CMOS. This is false. And charge present at the oxide semiconductor interface has strong impact on the threshold voltage. So this is also true. So three options are true, and option D is the correct option to go. Okay. Now this is also a simple problem associated with the what I can say with the scaling. Okay, you must have heard about the scaling, that we are continuously scaling down the transistor sizes in order to have maximum number of transistors per chip, so that we can reduce the cost, enhance the performance of the devices. Okay, there are many things, and you must have heard that once we reach a particular channel length, the devices are not able to get being we are not able to scale down the devices furthermore, and as a result of that we are looking into alternative device or architectures. Like for example, we had a planar structure previously. For example, when we studied a single gate device. Okay, then we can have a double gate device, that is there will be gate on the top as well as the bottom. Also we can have gate all around device. Okay, we can have the gate around the all the channel. Okay, so that is known by the gate all around device. In those devices we can scale even a bit further. Okay, and there are FinFETs. Okay, that is we are having three sides covered with a gate. Okay, so there are different kinds of architectures that help us to scale down the devices apart from the conventional scaling. So this problem says that we have a constant voltage scaling. uh, it is applied to a MOSFET with a scaling factor of 5. Okay, so as the MOSFET features are scaled down, what happens to the current in the MOSFET? So I have a table over here. Okay, I have kept it. I have copied it from somewhere, I guess online. Okay, so if we are doing a constant voltage scaling, it means that the supply voltage has to be kept constant. So that's what it is meant by 1 over here. So scaled parameter supply voltage remains constant. However, we are reducing the channel length. Okay, we are also reducing the channel width. Okay, we are reducing the gate oxide thickness. So all these things are reducing. Okay, so as a result of this thing, because we know W over L, they are reducing by the same factor, and C ox is epsilon ox by T ox. So to a first order, so if this T ox is reduced by 1 by alpha, it means that if T ox is reduced by alpha, so it means that the oxide capacitance is increased by alpha. So since this C ox directly comes into the in the term of the can say of the current, you can say for a constant voltage method, we will be having current which will be directly scaled by alpha. Okay, the current will scale by alpha, but this will have a serious problem. Okay, this will have this dynamic power will increase, static power will increase. So the overall power dissipation in this circuit what we are going to study will be enhanced. As a result, there will be heating of the device. Okay, so it is simple that if we are scaling a device by, but we are having one constraint, that is we are keeping the supply voltage constant, but we are reducing the channel length, it would degrade my, okay, it would degrade my power handling capacity of the device, because the static power and dynamic power both will be higher on the higher side, and because the current has increased. Okay, so as a result of this thing, you can say the current in the device has increased by a factor of 5, because we scaled all the dimensions by 5. That's we did the scaling factor, we used the scaling factor of 5. Okay, so the option A is the correct option to go. Now there is other method, okay, which you will see in this problem. It says that an NMOS transistor has the following parameters, that is channel length is 1, channel width is 10, oxide thickness is this, substrate doping is this, applied voltage is this. Now the device is scaled such that the scaling factor is this, and we have used constant field scaling. Okay, constant field scaling means that E, if E is the electric field, I should not write it like this. Okay, we have used early like this. Electric field is V over L. Okay, and V, let us say it is in the oxide. Okay, let me say E ox. Okay, okay, or if it is like some constant field I am talking about. Okay, let's talk about general field, but not in the semiconductor for the time being. Okay, so it will be some V in one dimension divided by L. Okay, so in I'm talking of 1D. Okay, in 1D case. Okay, let's assume for the time being this is just a bar. Okay, having a charge of negative negative and positive positive. Okay, okay, so the electric field will be constant in this. So if I have to enhance it, if I have to keep this field constant also. Okay, if I have to keep this field constant by reducing L. Okay, if E has to be kept constant, has to be, okay, sorry, if E has to be kept constant, but we have to reduce L, then we must be also reduced by same factor as L. Okay, as L. Okay, so it is clearly stated over here, if we are reducing the channel length by alpha, we will be reducing, where is it, okay, we will be reducing the supply voltage by alpha as well. So as a result, the total this field, as a result of this, the field is constant. Okay, the field does not change. So it says that we have to find the channel length for the scaling factor. So now if the previous channel length was 1 micrometer, and now L new, which is new channel length, will be, which will be simply 1 micrometer divided by 1.43. Okay, so it will be simply, so let me go to the calculator. 1.43 is simply zero point 0.7. Okay, it is 0.7 micrometer. Similarly, new width will simply be 10 micrometer divided by 1.43, which will be 7 micrometer. Okay, 7.7 and 7. Okay, so the option C is the correct option. So similarly for the TOX, what happens? TOX will also be reduced by the same factor. So the TOX in this case was, okay, 25 nanometer. So what would happen to the Tox is Tox will go by 25 by 1.43 micrometer. So it is approximately 25 divided by 1.43 is approximately 17.5 micrometer. Okay, I guess that was all about this thing that the previously we had left. Now I guess we will be mostly solving the problems related to the circuit. Okay, that is the small signal analysis. Okay, so the problem, this problem states that with the small signal resistance, that is dVb by dId in kilo ohms. Okay, we need to find it in kilo ohms by this n channel MOSFET is given by the n channel MOSFET shown in figure below, such that the V bias is 2 volts. Okay, and the transconductance parameter Kn is approximately, it is of 40 microamps per volt square. VTN, which is the threshold voltage for this N device, is 1 volt. So as a result of this thing, we need to find the dVb by, okay, dId. So from this, Vb is simply Vd. This is drain, this is gate also, okay, and this is source. Source is grounded, okay. So simply Vb is Vd is also Vg, okay, is 2 volts. It is simple, okay. Now VDS over here is given to be equal to what is it given to us? No, but there is one thing, VDS will be greater than VGS minus VTN, because uh, VDS is simply VDS and VGS are same, okay. VDS and VGS are same, and also and it is always that 0 is greater than minus VT. So this is also known by the name of diode connected node. Okay, this is diode connected, known by the name of diode connected. Okay, so let me write it like this: MOSFET is diode connected, and hence it will be always VDS will be greater than VGS minus VTH, and it will be in saturation always. Okay, so we need to find out dVb by dId, okay, which is also dVg by dId, and it is also 1 by dId by dVg, and it is 1 by Gm simply. Okay, it is simply 1 by Gm. So we know Gm is simply uh, now dId by dVgs, okay, dVgs, and Id is simply in saturation, okay, Kn by 2 Vgs minus Vtn whole squared, or Gm is simply dId by dVgs, so it will be Kn times Vgs minus Vt. Okay, Kn was 40 micro, I guess it was 40, and VGS is 2 volts, and VTN is 1 volt. VGS is 2, VTN is, so it is simply 1. Okay, so it would simply mean that dVb by dId is 1 by Gm is 10 to the power of 6 by 40. Okay, so it is simply 1000 divided by 40 is 25. Okay, so it's 25 kilo. Okay, yes. Okay, so I guess option B is the correct option to go. Okay, so Before going into the small signal analysis, let me insert some slides first. Okay, before going into the problem over here, let us first see how we build the small signal model. Okay, so how we go about building this small signal model. This is an important kind of an information that you should always have, and this is important for you to understand the even the small signal circuits. Okay, so in order to have a bit physical insights about this, what we will do is we will consider some this non-linear system, because uh, in order to have the power amplification, we need to have the non-linearity. Okay, so it's essential, because otherwise we will not be having this frequency translation. And also the resistive loads cannot have the output power greater than the input power. Okay, so we need to have, and as we know, this transistor is high, it acts as a non-linear device. So the MOSFET. Okay, so what we will do is we will consider some, okay, random non-linear system. So we will consider some random non-linear system. Okay, like this. Okay, let us consider a black box. Okay, and it has volts associated with it. This will be the I1 current which will be flowing in this device, and we will be having some voltage drop across these terminals. And let us say we have some load. This will be I2. This will be between some terminals 2 and 2 dash, and we will be having some supply voltage over this in order to bias this device. Okay, in order to bias this red black box, and we will be calling this third terminal as 3 prime, 3 and 3 prime, and this is our DC bias. Okay, now if we consider this as a black box, we can say the current I1 will be a function of three things. Okay, it will be a function of V1. Okay, it will be function of V2. Okay, let me write V2. V2 is over here, and also it will be a function of VDC. Okay, it will be a function of DC bias that we have applied. Okay, similarly I2 will be a function of V1, will be a function of V2, and will be a function of VDC. So now for this non-linear function, we cannot have a closed form solution. Okay, so what we will do is we will use the Taylor series. Okay, Taylor series is used in order to get some estimate of the functions by considering a particular operating point. Okay, so let us say we set some initial conditions. Okay, we set some operating options, uh, or can say operating points. Okay, so if we assume some operating points, like assume some operating points like uh, we can say that V1 is V1 of 0, and V2 is V2 of 0 at that operating point. Okay, and VDC is always constant. Okay, because it's DC supply, and as a result of this thing, I1 is I1 of 0, and I2 is I2 of 0. Okay, so now we can say that I1 of 0 is simply function of V1 of 0, V2 of 0, and VDC. Okay, this is simple manipulation, and I2 of 0 is simply function of V1 of 0, V2 of 0, and VDC. Okay, so this we now, what we do is we now perturb our system. Okay, by perturbing, what we mean is we add some small voltage to these V1 and V2. Okay, so as a result, okay, so as a result of this thing, what we do is we now perturb our system by applying small voltages. Okay. So what we do is that we change the V1 from V1 0 plus delta V1, and we change the V2 to V1 V2 0 plus delta V2. Okay, we do not change the supply voltage because supply voltage does not fluctuate. Okay, so it is mostly constant for the device. Okay, so now if I write down the Taylor series expansion for the I1, first of all we will be having simply the term at the initial operating point, which will be V1 of 0, V2 of 0 and VDC. Now we will be having the derivatives of this function with respect to the V1, okay, at constant V1 0 and V2 0 times delta V1. Okay, what I am doing, I am simply using the Taylor series expansion. Okay, and df1 by dv2. Okay, so it is the change of the function 1 with respect to v1 and change of the function 1 with respect to v2 with the initial conditions set to v1 0 and v2 0. And similarly we will be having higher order terms like d2f1 by d1 dv1 delta v1 square by 2 factorial actually plus so on. Okay, but the thing over here is that only this will be associated with the desired frequency, that is omega naught. This will be having the frequency of 2 omega naught. Okay, and we do not want we want the amplifier to behave in the linear region. Okay, we want it to be a linear. Okay, so we want to suppress all the higher order components like 2 omega naught, 3 omega naught. Okay, so we do not want the higher order components, we just want the desired signal. Okay, the signal which is at omega naught frequency. Okay, otherwise we will be having lot of signals with different frequencies being the multiple of the omega naught. Okay, so what we do is we simply what we do is we simply do first, let me write down this I1. This I1 is simply now I1 of 0 plus delta I1, and this thing is simply I1 of 0. Okay, this thing is I1 of 0. Okay, you know that. Okay, plus df1 by dv1 times delta v1 plus df1 by dv2 delta v2. So what we do is without which we want to suppress the higher order components, so we want to ensure that df1 dv1 times delta v1 df1 dv2 delta v2 has to be much greater than d2 f1 d1 square delta v1 by 2, this is squared, plus d2 f1 d1 square by 2. Okay, plus rest. So we do not need these. Okay, so as a result of this thing, we ensure that this part is significant. Okay, is significant. Okay, so so in order to represent the input signal at the output without having these additional frequency components, we need to ensure this thing that these, although this is ideally what I am speaking about, I am being idealistic all the time. Okay, so as a result of this thing, you can clearly write the equation like this. Okay, we have neglected the higher order components. Okay, so it would give me delta I1 simply equal to df1 by dv1 times delta v1 plus df1 delta v2 into del v2. Okay, so we have to get the signal only at the frequency that we gave to the input signal. Okay, the input signal frequency should match the output signal frequency. So as a result of this thing, we should have only the linear terms. Okay, so similarly delta I2 can be written as df2 dv2, sorry, dv1 will be first. Okay, dv1 delta v1 df2 dv2 delta v2, and all these are at constant operating points v1 0 v2 0. I didn't wrote it for all the cases because it was understood v1 0 v2 0 v1 0 and v2 0. So this delta I is the small signal change in the current. Okay, so I can simply write it as delta I, and this df1 by dv1 is simply y11 times this delta 1 is the small signal change in the v1. Similarly, this df1 times dv2 is simply y12. Okay, be careful about these things. This is 1, this is 2. Okay, that's one dy, and this is y12. Okay, y12 times v2. Similarly, I2 will be simply y21 v1 plus y22. So if we write down this now in this matrix form, it will be simply I1 I2 is simply y11 y21 y12 y22 v1 where these are the incremental changes in the voltages. Okay, so if I draw this, if I draw the electrical representation of this network, okay, so it will be simply like this. It will be like this. I will be having y11. Okay, this will be my v1 change, that is delta v1. This will be my I1. Okay, this will be my y12, which will be controlled by the v2, that is the voltage at the output source, and this will be my y21. It will be controlled by the v1. Okay, the v1 voltage source, and also I will be having y22. Okay, and on top of that, this is I2, and this will be v2. Okay, this is our v2. Okay, so it is simply uh, uh, these are actually voltage controlled current sources. Okay, both. Okay, so this is the two port network. uh, Electrical two port network representation, two port network in an electrical form, representation form. Okay, so this is what we have obtained. We have obtained a device where we are having these voltage controlled current sources. Now if I now apply some voltage to the input, that is I have some signal, and also I have some load at the output, and I transform the conductances. Okay, it is like what I am talking like this. Okay, I'm talking about the circuit like this. Okay, if this is our Vs, which is the supply voltage, and this is our Rs, So I have attached some network to this two port network. I have attached an input signal which is having resistance Rs associated with it, and this will be our Y11. Okay, this will be our Y12, V2. This is I. Okay, this is Y21, V1. This is Y22, I2. This is V2, and now I am connecting some load to it as well. Okay, this is our RL. Okay, so this is a resistive load we are trying to drive. So it will be better for us to have the RS in terms of the conductances. So this is a sample case. Okay, this is a sample case. This is a sample case for the above problem now. Okay, we need to check whether we will be able to have some gain from this circuit. Okay, what we designed for this two port network. Okay, so let us draw the this whole thing in terms of conductances only. So the resistance will become conductance, which is represented by GS, and the current source will represent by Vs times GS, and it will be simply this thing, and this GS will come in parallel with the Y11. Okay, and this will be simply our I1. This will be Y11. This will be Y12, which is controlled by V2. Okay, this is our V1. Okay, this is not associated with this thing. Okay, this is V1. Okay, similarly we will be having Y21, which is controlled by the voltage at terminal 1. This is Y22, positive negative V2. This is our load resistor. Okay, so what we can do is we need to find out the voltage gain. So voltage gain is simply V2 by Vs. Okay, so it is V2 by Vs. So for that, let's use the KCL first. I1 is simply given by okay, I1 is simply this current and this current summation. It is simply Vs times Gs minus V1 times Gs. Okay, and also I1 is simply equal to V1 times Y11 plus Y12 V2. Okay, so if I equate 1 and 2, what I will get is I will get Vs Gs plus V1 Gs is V1 Y11 plus Y2. So sorry, it's minus. Okay, so it's minus. So it is simply Vs Gs is Y11 plus Gs times V1 plus Y12 V2. Okay, so this is our equation 1. Okay, and I2 is simply the current flowing in this region, in this part of the circuit, and it is simply I have represented the conductances, resistances with the conductances, so it should be GL. Okay, so it is simply minus V2 times GL. Okay, actually the current I2, if I consider the current I dash is V2 times GL, and I2 is minus of that current. Okay, So it is simply minus V2 GL is simply equal to I2 is also equal to V2 times Y22 plus Y21 times V1. Okay, or if I use these equations, I can say, if I equate these two, I could say that 0 is simply equal to Y21 V1 plus Y22 plus GL times. So this is our equation 2. So we got the two-port network representation of the system. Okay, when we have this load as well. Okay, so it will be simply like this. It will be uh, the equations will be like this. It will be Vs times Gs 0 is equal to simply Y11 plus Gs plus Y12. So it is Y12 over here. Okay, it is Y21. It is Y21, Y22 plus GL. Okay, this V1 and so now let us do some mathematical representation, and that now let us get the value of V2. V2 will be simply, it will be simply Y11. You must have heard about this, solving this matrices by using the Cramer's rule. So it is GS Y21. So I have to use V2. So I will replace the second column with VSGS 0. Okay, divided by the determinant, which will be Y11 plus GS Y12 Y21 times Y22 plus GL. Okay, so it is simply this V2 is simply now it is simply now minus times Y21 GS times VS divided by Y11 plus GS times Y22 plus GL minus Y21 Y12. Okay, so this is okay, this is the expression what we obtained for the V2, and let me write it for V2 over Vs simply. So it will be V2 over Vs will be, sorry, V2 over Vs will be like this. So now we want to maximize the gain. Okay, so in order to maximize the gain, what we can do two things. We can make this thing, okay, we can make this thing equal to 10 to 0, or we can make this 0 itself, so that we get the infinite gain. But this cannot be 0, this can't be 0, otherwise we will have oscillations. Okay, because the system will now not be stable. Okay, we will be having oscillations. Okay, if we try to make this 0, we will be having self-sustained circuit. That will be we will be getting some output even we do not have some input. So what we will do is we will try to minimize this. Okay, and try to bring it close to 0, not exactly 0, and we will try to bring it close to 0. Okay, so what we can do is we can say we can make we can make use of this thing, like this V1 by Vs is, let me write it again, minus 121 times Gs divided by Y11 Gs Y11 plus Gs times it was Y22 plus Gl minus Y12 Y21. So what we can do is we can uh, we can make this Y12 to be equal to 0. Okay, we should have a circuit like this. For ideal conditions, we want this Y12 to be equal to 0, and also Y11 and Y22 to be equal to 0. Okay, so if we have these all these things to be equal to 0, and also we want to maximize Y21, okay, maximize Y21. So if we have all these things to be equal to 0, V1 by Vs will be simply minus Y21 Gs times Gl. Okay, so Gs and Gs will go, and V1 by Vs will simply be minus Y21 times by Gl. Okay, so this will be the maximum gain. Okay, so this is maximum gain we can get gain, but we have some conditions, but we have to ensure that Y12 is equal to Y11 is equal to Y22 is equal to 0, and Y21 is as high as possible. Okay, so if we now draw this ideal network, two-port network, it would look like this. Okay, let me insert some slide. So what we have said that in order to maximize, let me write down it like this: in order to maximize, okay, V2, we don't want the current to flow through Y22. Okay, that's what we want. We want Y22 to be equal to 0. Okay, and we do not want current division. We want all the current to flow through Gl. Okay, and also we want this we do not want this V1 should drop across this there should be no current division across this Y11 also. Okay, so the ideal network should look like this. So this is Vs, this is the source resistance associated with the source what we are using, and this is V1. We want Y11 and Y12 to be equal to 0, and we want this Y12 V1 to be the maximum, and we want it to drive the load GL such that we are having a maximum gain. So this is our desired incremental model. Okay, so this is our desired incremental model, and this is what you mostly use. Okay, considering an ideal amplifier. Okay, so this is what you say that we want to have the maximum gain, and as a result of this we want to have a voltage controlled current source. Okay, this is what it is voltage controlled current source controlled by V1. Okay, the signal we are applying at the input, and we are getting its amplified version at the output. Okay, so this is the ideal how you derive the small signal model for this ideal MOSFET or ideal amplifier case. Okay, so we can solve for the this MOSFET in the, let's say, in the non-saturation region as well as in the can say in the saturation region. So it should like look like this. So if we draw the MOSFET, okay, if we draw the complete model for the MOSFET, and let me write the problem like this. Question is like this: we have to find y11, y12, y21, and y22 for MOSFET in non-saturation and saturation region. Okay, so let's write down the equation for the ID. ID is the drain current. It is simply mu times Cox W over L VGS minus VTH times VDS minus half of VDS squared. Okay, so uh, we have to find the uh, let's first draw the small signal model. So this is VGS. Okay, this is VGS, this is Y11, this is Y12 VDS. Okay, this is Y21 VGS, this is Y22 positive, negative VD. Okay, and this is the current IDS, and this is the current IGS. Okay, so Y11 is simply DIG by DVGS. Okay, but IG is 0, gate current is 0, so it will be 0. Okay, so Y12 is DIG by DVDS. Okay, and also the gate current is 0, so Y11 and Y12 will both be equal to 0 in non-saturation region. Okay, so I'm talking about in non-saturation. Okay, in non-saturation both are equal to 0. Now Y21 is simply it is DID by DVGS at constant VDS. So it is simply if I derivate this equation, I will get simply mu times Cox W over L times VDS. So Y21 is a linear function of VDS. Okay, so Y21 is a linear function of VDS in non-saturation region. Okay, and similarly Y22 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 is DID by DVDS. It is simply mu times Cox W over L VGS minus VTH minus VDS. Okay, so this is Y22. Okay, so this Y22 is not equal to 0. Y22 is not equal to 0 in non-saturation. Okay, so but we want this Y22 to be equal to 0. Okay, so you must have heard that we operate the MOSFET in the saturation region, because for in that region also the Y21 will be the maximum, and also you can say this Y22 will be equal to 0, which we will see. Okay, so now let's use another color in saturation. Okay, so in saturation Y11 will be still 0 and Y12 will be still 0 because gate current is 0. Now Y21 is simply dID by dVGS, and di and IDS is simply 1 by 2 mu C ox W over L VGS minus VTH whole square. So dID by dVDS will be simply mu times C ox VGS minus VTH, and Y22 will be dID by dVDS. Okay, sorry, it is dVGS in this case. And so simply this is for the ideal case, this is independent of VDS, so Y22 is ideally 0. So what you have seen is that in this saturation region we can ideally get the maximum gain, and as a result of this thing, uh, because there are some limitations as well, that is, like for example, this a power supply will limit our VDS value. Okay, that is the maximum this GM or gain value, this transconductance value we will get, and the gain is dependent on this Y21, and it will be most of the times dependent on the power supply voltage itself. So as we can see that this MOSFET, if we bias it in the saturation region, we will be having ideally this Y22 to be equal to 0, and we will be able to achieve the maximum gain. So we can write it like this: to achieve maximum, okay, maximum possible gain, we bias the MOSFET in saturation, because since it maximizes the Y21 and minimizes, ideally it should be 0, but in the real cases it isn't, and minimizes Y22. Okay, so this is the main reason why we bias the transistor, or sorry, this MOSFET, a transistor MOSFET one in this thing, in the saturation region. Okay, now we have seen the small signal equivalent model of the MOSFET. Okay, now we are good to go with the problems. Okay, so we can solve any problem now which will be associated with the small signal analysis. We have seen how we can build the incremental model from just a black box and obtain a maximum gain from this. Okay, and we know that the MOSFET is a voltage controlled current source. It behaves like a voltage controlled current source. So we can effectively draw the small signal models for all the transistors. Okay, but all the MOSFETs that we are going to study. So the problem now in hand is, it says that we have a circuit in the figure, and we have to consider the channel length modulation. That's where Y22 will not be 0 now, because Y22 will now be dependent on the VDS. This is the main factor that comes into the picture, and we will be having this Y22 which will be now VDS dependent. Okay, uh, so Y22 is basically now the resistance which comes into the picture at the port between port 2 and 2 dash. Okay, so it will you must have seen that the current does not saturate with the VDS, and as a result of this thing we will be having some linear kind of a increase in the current even after the saturation region. Okay, so if I now all transistors operate in saturation, that's what we have seen. In order to have the maximum gain, we need to operate them in the saturation, and we have to we have negligible body effect. Okay, the AC small signal voltage gain has to be found out, which is V naught by V in. This is our V out, and this is our V in. Okay, so let us what we can say, Okay, so let's draw the small signal equivalents of these. Okay, so basically this is a PMOS, this is an NMOS. Okay, this is also NMOS. Okay, so this is how we represent the PMOS. Okay, okay, this is PMOS, this is NMOS. So if we now draw the small signal equivalent for this, let me use another slide for the same. So let us draw it for the PMOS first, which is M3. So all the DC sources will be grounded for the small signal analysis. Okay, and all the current sources which will be independent current source, will be open. Okay, so let's be clear about this thing. Okay, so VG is now connected to some supply voltage, which is, it will be now grounded. So it will be like this. If this is our VG at the you can say at the for the M3, this is our VG. Okay, and the sources will also be grounded for this PMOS. Okay, because it's connected to the VDD. It is source for PMOS, it's gate for PMOS, and it's the drain for PMOS. Okay, okay. So the source will also be grounded. So this is a source. Okay, so as a result of this thing, we will be having just the channel length modulation effect of this R03, because VSG is equal to 0. So there will be no current source which will be dependent on the V1. Okay, so we will be simply having V1, which will be having the drain on the attached on the drain of P, and it is VDD. And for the other MOSFET, which is NMOS, we are having the gate connected to the, again gate is connected to the ground. Okay, okay, and this is the source of that NMOS, source of NMOS, and it is having some dependence GM times VG SN2. This is GM2, I guess. Yes, it is the second transistor, and it will be having also a resistance associated with it due to the channel length modulation. It will be R02, and its drain is also connected to the ground. Okay, so this is the small signal equivalent for this NMOS. Okay, NMOS2. Now the source of this MOSFET is connected with the drain of the M1. Okay, okay, this is our M1 MOSFET. Okay, and this M1 is having Vi at the uh, gate. Okay, and it is having some GM1 VGS1. Okay, times R01. This will be V0. Okay, yes, I guess. Okay, this is our uh, small signal equivalent for all the three transistors and for the whole system. Okay, so now this VGS1, VG, I have used capital, I should have used small. Okay, this VGS1, VGS2, VGS1 is simply Vi. Okay, so now this will be, there will be some current flowing through this current will be flowing like this, there will be some current like this, and there will be current, some current like this. So if I use the KCL now, okay, so if I use the KCL now, what I will obtain is, I first at this node I am having current which is flowing from 0 minus, since this is grounded, V0 by R0 of 3 is plus, I am having a current which is flowing from this, and these currents are adding up to this. Okay, so this is GM2, and VGSN2 is simply VGSN2. VGSN2 is simply 0 minus V0. Okay, yes, so it is simply VGSN2. So let me write it minus V0. Okay, plus this is 0 minus V0 minus V0 by R naught of 2 is equal to this current GM1 VGS1. VGS1 is VI, plus this current will be V out by R naught of 1. Okay, yes, so it is simply minus V out, not V out, I have used V0, minus V0, okay, 1 by R01 plus 1 by R02 plus 1 by R03 plus GM2 is GM1 VI. Okay, or simply, sorry, oh, or simply V0 by Vi is minus GM1 1 by R01 plus 1 by R03 plus 1 by R02 plus GM2. Okay, so this is the answer we get, but we have to represent it in this form, like we have this parallel combination of the resistors and the impedances. So we can clearly see that 1 by R01 parallel R03 is simply 1 by R01 plus 1 by R03, and 1 by R02 parallel 1 by GM2 is 1 by R02 plus G2, and these in parallel will simply be that if this is 1 by R01 parallel R03 parallel R02 1 by G2 is simply equal to 1 by R01 parallel R03 plus 1 by R02 1 by GM2. So V0 by Vi is simply minus GM1 R01 parallel R03 parallel R02 parallel 1 by GM2. Okay, so that's what it is. Okay, okay, that's what it is. Okay, option C is the correct option to go. Okay, now, now moving to another problem which is associated with this. Also, this is also associated with a small circuit, a small signal circuit. But before that, let me have some water. So we have a circuit which is shown in the figure for two transistors, that is NMOS and PMOS. and for this NMOS, actually they are both NMOS. Okay, they are both NMOS. Okay, this is not PMOS. So this is NMOS, this is also NMOS, and we need to find for both the NMOS transistors, they are both identical with threshold voltage being 5 volt, and we have to neglect this channel length modulation, and we have to consider the output voltage. What would be the output voltage V out? Okay, so uh, this MOSFET is clearly in saturation, so the current has to be same for the both. Okay, so the other MOSFET, for the other MOSFET we need to also have the saturation. Okay, so if I have the saturation for the MOSFET 1, which is having W by L mu n C ox VGS, this is VGS for this thing is simply uh, uh, it is simply VG 1, which is 30 volt. VGS is VG minus V out, VG minus VTH. Minus VTH whole square is equal to W by L mu n C ox. VGS for this MOSFET is simply 10 minus VTN is 5 whole square. So this thing and this thing will go, and this will be 25 minus V out squared is 5 whole square, or simply it is 25 minus 5 is V out, or V out is simply 20 volts. Okay, so the option B is the correct option to go with. Okay, I guess I deleted the wrong slide. Undo. Okay, let's not delete any slide. Okay, so now moving to the question 4. Okay, this is NMOS, this is also NMOS. Okay, both are NMOS, and we have to ignore the channel length modulation and find out the small signal voltage gain. Okay, when a W by L for the M1 and M2 are different. Okay, we are having two different W by L's. Okay, so let's draw the small signal equivalents for both. uh, so this is the gate is grounded for the small signal, drain is grounded. Okay, so this for this we will be simply having uh, the gate is grounded. Okay, this is the gate, and we will be having GM2 VGS2 with this being grounded, GM1 V in, because V in is applied at the gate. Okay, and this will be grounded. Okay, this will be grounded, and this will be our V out. So you can say simply that GM2 VGS2 is simply minus V out is GM1 V in. Okay, or simply V out or V in is minus GM1 by GM. So we have got the values in terms of the GM. Okay, now we need to write the GM in terms of the W over L. Okay, so for that let's do some mathematical manipulations. Okay, so in saturation, okay, in saturation this drain current is simply 1 by 2 W over L mu times C ox. VGS minus VTH whole squared. So GM is simply W over L U times Cox VGS minus VTH. Okay. From this equation one, we can write this VGS minus VTH to be equal to 2 times ID by mu times Cox W under root. Okay, so I have used this. Okay, so this GM is simply equal to this thing. Okay, yes. So if I now write down this, if I multiply and divide by this GM by 2, if I multiply it by 2 and divide by 2 and also multiply it by VGS minus VTH once and divided by VGS minus VTH, okay. So what I will get is, this is simply ID. So GM is simply 2 times ID divided by VGS minus VTH. So now put this ID, now put this VGS minus VTH over here. Okay, so the GM is simply 2 times ID divided by root 2 ID times mu times C Cox W. Okay, so it will be simply 2 times ID mu times Cox W with a square over it. Okay, so this is the GM in terms of ID and W over L. Okay, now for this problem, ID1 is equal to ID2. ID2 is equal to ID1. Of course, the circuit has to be complete. Okay, the same current has to flow throughout the circuit. Okay, so this is what I am talking about. This ID1 has to be equal to ID2. That's what we did over this point at the when we use the KC. Okay, so V01, V0 by Vin is GM1 by GM2. Okay, GM1 by GM2. So what we can do is, can simply say, okay, this GM1 by GM2 is V out by Vin is equal to 2 times ID1 mu times Cox, because the transistors are identical except for the WL. W1 by W2, 2 times ID2 mu times Cox W over L by 2. Okay, ID1 is equal to ID2, ID1 is equal to ID2, mu and at Cox are same, this and this is same, so we are left with minus W by L of 1 divided by W by L of 2. So it is simply 40, it is 80 by 100, 80 by 20, not 100. So it is simply 80 by 20 with a minus sign. So it's minus. So this is a simple result. What we have derived in this case is that GM is GM in terms of the current we found out, and also we found out that if we have this diode connected load with our connected with our M1 amplifier, where the source is grounded, and we have this common source configuration. Okay, as a result of this thing, and in that common source configuration we had no load at the no resistor connected to the source, or the no resistor connected to the gate, etc. So the voltage gain or the signal gain is simply equal to minus gm1 upon gm2. And from the expression, what we found out, that for the identical cases, for mu and cox to be same, we found out it is simply the ratio of the w over l's. Okay, and as a result of this thing, uh, we obtained uh, uh, the value for the gain to be equal to minus 2. Okay, so let's move to another problem. Okay, so let's move to another problem. which says which says that we have to consider the circuit with threshold voltage 1.2 volt and L1 and both L1 and L2 are equal, and we have to ignore the channel length modulation. And after that, we have to find the ratio for the W. Okay, so this is diode connected, this is also diode connected, so it means that both the MOSFETs are in saturation and the current will be same for both the MOSFETs. So both are in saturation, and as a result of this thing, we will be having current to be equal to 1 by 2 mu n C ox W over L. For the transistor 1, it is simply VGS is 1.5 minus VT is 1.2 whole square, and it is equal to 1 by 2 mu n C ox. Okay, so it is W over L 2. VGS is simply 3.5 minus 1.5 minus 1.2 whole square. So it is 2 minus 1.2, it's 0.8. So it's simply W1, because L1 and L2 are same. So it is W1.3 whole square is W2.8 whole square. Okay, so it's 8 by 3. Simply 8 into 8 is 64 by 9. 64 by 9 is let me write it down. 64 by 9 is 7.1. 7.1. So it is W1 by W2 is simply 7.1. Okay. Uh, so let's move to other problem, which says that we have to consider a circuit as shown in the figure, and in this figure the threshold of the device M1 is 0.5 and V input is 1 volt, and DC voltage at the output is 1.5, and mu and Cox value is given to be equal to 0.1, and there are many other parameters that are given. We have to find the current throughout the MOSFET device. Okay, so it is simple. The current will be divided like this. So I can use the KVL and KCL. Let's use the KCL at this node. Okay, so it is simply 3 minus V out by 10K is equal to V out minus V in by 10K. Okay, V out will be right over here. Okay, plus ID. ID is the current flowing through the transistor, through the MOSFET. Okay, so it is simply ID is simply equal to v out is simply 1.5, v in is 1, so it is 1. So it's 2 minus 1.5 is 1.5 minus 1. Okay, so it is v out is 1.5, so it's 0.5 by 10k, so it is simply zero point 0.5, it's 1, it's zero point 0.1 milliamps. Okay, so it's option B. What we have done is we have simply used the KCL at this node. Okay. Oh, what has happened to it? Okay. So with respect to the question 6, we need to find the W over L. Okay. So W over L in MOSFET, for the MOSFET in saturation, is simply ID is 1 by 2 mu n C ox W over L VGS minus VTH times 1 plus lambda VDS. Okay, I have taken lambda because it has give. Okay, that's why I have taken lambda and VDS dependence of the saturation curve. Okay, so so it is simply zero point 0.1 milliamp is simply 1/2 of this mu and Cox is given to us. I guess it is zero point 0.1 mega. Okay, it is zero point 0.1 into uh, zero point 0.1. Okay, so it is zero point 0.1 into 10 to the power of minus 3. Okay, W over L VGS minus VTH is simply VGS minus VTH is 1.1 minus zero point 0.5, so it is 0.5. It's zero point 0.5, so it's actually whole square, 0.5 whole square, and this is 1 plus lambda is 0.09 times VDS. VDS is 1.5. Okay, so if we solve for this, all things will go, this will go, this will go, so it is simply 0.09 into 1.5 plus 1, 1.135 into 0.5 into 0.5 to 1 by 0.14, so it's W by L is approximately 7. It's approximately 7. Okay, so none of the options match, so we'll select none of these. So I guess that's it from my side. Okay, no, we can do this. So when used as an amplifier, a MOSFET is biased in. Okay, it's biased in saturation. We have seen we did a long derivation for this in order to maximize the gain and in order to have the output resistance associated with the MOSFET minimal. We need to operate it in the saturation region. Okay, so it's correct. So MOSFETs are, what are they? This we also did. They are voltage controlled devices with high input impedance, because we do not want the we want whole signal to be transferred. Okay, we do not want any signal drop. Okay, so we want the voltage controlled devices with high input impedance. Okay, so we have this thing, and we want all no signal to be dropped at the output as well. And what is this? This says that the effective channel length of a MOSFET in saturation decreases with increase in drain bias. Okay, this we have seen previously, that how does this pinch off point occur and how the current saturates, and how after the saturation there will be this high field that will sweep the carriers from the uh, point where this channel was pinched off into the drain side because of the high electric field. Okay, so what we did today is we mostly solved the problems associated with the circuits, and we I guess did it over here. Okay, so this was the main thing which we solved today. That is for in order to have this voltage gain, we first of all said that we need to have this uh, a time non-linear system where we will be having this gain of this, where we'll be having the power gain, and the power gain should be such that the signal frequency given in the input should also be having the same frequency at the output. That is, if I am giving a signal at frequency omega naught, the output signal, which will be amplified in nature, which will should also have the main component with frequency at omega naught itself. So for that, we used some conditions. We said that we are perturbing the system with some small signal delta v1 and delta v2, and then use the Taylor series, and also assumed that we tried to superimpose some condition, that is this dfv1 times v1 delta v1 is plus df1 by dv2 times delta v2 is much greater than the rest of the components, so that there will be the signal separation of the higher frequencies. Okay, so from that we obtained some small signal model in terms of the y parameters. Basically these y11, y12, y22, they are y parameters. Okay, and for that we considered a sample case where we considered these resistances, and we considered the input resistances and the output load resistance, and we maximized the total gain, and we obtained the expression such that the gain is dependent on the output resistance only. Okay, times the gm, which is the y21, the transconductance. So we tried to maximize this gm for the this y21 for the MOSFET, and we found out that it will be in the saturation region, that this gm will be having the maximum value, and also for that case the y22 will be 0. Okay, so for that case the y22 will be 0, and that is the ideal case. Ideally it will be having some resistance associated with it, but in the saturation it will be minimal kind of thing. Okay, so I guess that is that then we solved the problems associated with the small signal model, and uh, yes, absolutely. Okay, so I guess that is it from my side for today. So let's end today's session. I guess there are no queries, so thank you for joining this session.